Jai Hind. Today we are going to discuss an advanced data structure, that is AVL trees. In this particular topic, we'll talk about what are height balance trees, then what is AVL tree, why we use AVL tree, what else we need to pay when we are using this height balance trees, and how do we do it, that is with help of balance factor and rotations. And then we'll talk about different type of rotation, single rotation and double rotation, and finally we will conclude with an example of building an AVL tree. So first of all, AVL tree is a binary search tree. What is AVL tree? It is the balanced binary search tree, and the name is after the discoverers A for Adelson, Valesky and Landis. Now what is AVL tree? When we have a binary search tree, we all are aware that in binary search tree at a particular node, the value is less than equal to all the values of nodes of right subtree and greater than the value stored in the left subtree. Now when we have these values stored in binary search tree, it may be the case that the values are coming for insertion in binary search tree in increasing order. So if I am getting these values 1, 2, 3, 4, so when I will insert these values in binary search tree, it may create a binary search tree with maximum height. For example, if I consider the insertion 1 first, then 2, it will be inserted in right side, then 3, as 3 is greater than 2, will insert this in right subtree, right child, then 4. So we can see here that binary search tree are used for fast searching, but when we see this particular order, we can see that it is just comparing all the values in worst case 1, 2, 3, 4, just we do in linear search. Okay, so we can add some additional balance condition to this binary search tree, that is our AVL tree. The balance condition must be easy to maintain and ensure that depth of the tree is order of log n. We want to avoid this ON. This is one of the possibilities binary search tree, but what we want to do, we want to ensure that the depth doesn't reach to the comparison do not reach to the order of n. We want is to just log n. So to ensure this, we use the height balancing. An AVL tree is a binary search tree that is height balanced, meaning that it has two properties. The first property is at every node, the subtree of the node must differ in height by at most 1. So what are the subtree? If I consider this particular node, it is having two subtrees, left subtree and right subtree. So the maximum difference in the height should be just 1. So we are allowed two values, 0 or 1. Every subtree of this tree is also AVL. It means when we are talking about this node, this one is its left subtree. Now for this node also it should be AVL, means this property should hold for each and every node, then it is AVL tree. Height balance tree. We know that height is the longest path from a root to a leaf. So if we are having height balanced K tree, it means it is having the property of HBK. It means the difference between the left subtree height and the right subtree height is not differing more than K. It means the distance must be at most K. So what is AVL? In AVL we said that the the left subtree as well as the right subtree should have the height difference between 1 only, less than 1 only. Okay, so 0 or 1, less than equal to 1. So it is height balanced of 1. HB1 tree is called AVL. We can have any level of balancing. So if we have 2 difference, then that is HB2, but in AVL we have at most 1 height difference. So that is our AVL tree. Let us understand with example. If I consider this, so is it AVL tree? So if I consider 3, at 3 the left subtree and right subtree height is 0, so it is 0 and 0. Okay, 4 the height is 1 and 0, left subtree 1, right 0. For 2, 2 and 1. So when I am checking all the heights of 5, 4, 3, 7, I am only getting the difference 1 or 0. So it is AVL tree. The height balancing is there. Okay, if I consider this one and I check 3, at 3 the height is 1, 2, 3 and the right side height is 1. So left side is 3 and right side is 1. So the distance is 2. So this is not desirable. This is not AVL tree. So this way we can see that by checking the difference of heights of left subtree and right subtree, we can tell that it is AVL tree or not. Why do we want AVL trees? What is use of AVL tree? When we have binary search tree, as we discussed on one slide in starting, that the binary search tree structure is highly dependent on the order of insertion. So if I am having order of insertion in ascending order, so it will be having it will reach to the maximum height. So in worst case, the maximum height binary search tree is considered. In that case, insertion, deletion and searching operation will have order of n complexity. But if we do height balancing, the height balancing will maintain the maximum height to log n to the base 2, because it is binary tree. So the most important we should remember is AVL tree is binary and it is binary search tree. Okay, in this case the insertion, deletion and search operation will be order of log of n. So for very large n value, this difference is very, very high. So because of this, the complexity order of log of n is highly less than order of n, very, very less than the comparison of, in comparison it is very less than the worst case complexity of binary search tree. That's why we go for AVL trees. Now another important point, when we talk about AVL tree, in AVL tree what we are doing insertion like binary search tree. But if I consider this, in binary search tree, when I was having 1, 2, 3 insertion order, I inserted 1 in binary search tree, then 3, 2, then 3. So binary search tree is formed. But when I am talking about AVL, in AVL what is there? We do insertion, and when we do insertion, we check the state of this balancing. So when I inserted 1, the balance was okay. When I inserted 2, the balance was okay. But when I inserted 3, now AVL trees, it is no more AVL tree. So I need to adjust the height. So that is the added complexity. When I am doing insertion and deletion or searching, so an additional amount of complexity arises during the insertions and deletion, because one insertion or one deletion may create the height difference of 2, and what we desire the difference of 1 or 0. So in this case, this was the situation when the difference was 0 and 1, left and right subtree height distance was 0 or 1. But when I inserted 3, then what happened? at one node the difference became 2. So it is no more an AVL tree. So we need some balancing. So that is the added complexity. We have shown here the same point in this slide. I was having this height balance tree here at 5, 2 and 1. So difference was 1. Left subtree height and right subtree height distance was 1. At 4 also it was 1. At 3 and 7 it was 0. But when we inserted 1, what happened at 5? The left subtree height became 3 and right subtree height was already 1. So the difference became 2. So what we need some balancing here. So that is the additional cost that we need to pay. That is the additional complexity added to the maintenance of AVL tree. Same way in this case, if we delete 7, this will be the resulting tree which is no longer an AVL tree. So again we need some balancing. So these are the violations that we need to take care. So how do we will take care of these violations? We will define a notation that is called balance factor. What is balance factor? Balance factor of a node is left subtree height minus right subtree height. The difference between left subtree height and right subtree. So what is desirable in AVL? Left and right height distance should be at most 1. It means 0 or 1. So if we will calculate this value, it means the difference will be either -1, 0 or 1. So the distance must lie between -1 and 1 for all the nodes. So this balance factor we will use to check after insertions and deletions, to check is there any violation occurred. If some violation occurred, we need to reference that. We need to maintain the balancing. So how do we check the balance factor? If I consider 1, the left subtree height is 0, right subtree height is 0, so 0 minus 0 is 0. If I check 3, at 3 left subtree height is 1, right subtree height is 0, so the difference is 1. If I consider 11, for 11 the left subtree height is 0 and right subtree height is 1, so 0 minus 1 is -1. At 10 also, if I see the left subtree height is 1, right subtree height is 2, so 1 minus 2 it will be -1. Okay, so we will check all the values. So in this, when we are checking all the values of a balance factor of 8, we are getting 0. For 4, 1, 10, -1, 3, 1 and so on. All the values are either 0 or 1 or -1. So it is AVL tree. So we will use balance factor and we will check is there any violation or not. If after insertion and deletion any of these become other than 0, 1 or -1, we need to maintain the AVL tree. This is one example of invalid. In this, the balancing factor of 8 is 2 minus 0, so 2. For 4 it is 1 minus 0, 1. For 3 it is 0 minus 0. So what is there? For 8 the balancing factor is 2. So it is not an AVL tree. So now the important point is, when we are getting the balance factor 1, -1 or 0, it means it is still an AVL tree after some insertion or deletion. But if it is not, okay, for example this, if we consider here the balancing factor will be 0, here the balancing factor is +1, here the balancing factor is +2. So now after doing some operation in intermediate level, what we are having, we are getting a balance factor 2. Okay, so now we need to maintain this balance. So what is done for this rotation. What is a rotation? A rotation is an operation to rearrange nodes to maintain balance of an AVL tree after additions or removals, means inserting nodes or deleting node. So that is our maintenance of balance using an operation. That operation is rotation. Okay. Now, what type of rotation will do? There are two ways to do the rotations. It may be single rotation or double rotation. When we have single rotation, that can be left rotation or right location, and for double rotation it could be left right or right left location rotation. Now see, what we are having, the structure will tell us it will use left rotation or right rotation. So when I consider this one, I can see that this is unbalanced node. What is balancing factor of the upper node? That is +2. Okay, it is +2, and the disturbance, the failure of balancing is because of this left +1. So both are having same difference, same signs. If I consider this one, here also the disbalancing, unbalanced is because of this branch, and when we see this branch here, again I am getting the same sign. Okay, so if these are the disturbing nodes, the disturbed balanced nodes are having the same sign, okay, then we do single rotation. Okay, we are calling it violent node. When the violent node has positive balance factor, then we see its left child. Left child we check for positive. If we are having positive and we check the left child, if that is positive, then we do single rotation. Same way, when it is negative, then we see the right child node. If that is also negative, then also we do single rotation. And if the violent node is positive, okay, but its left child node is having opposite sign. Here it was +2 and the left child node is having the opposite sign. Same way, if it is negative and right side is having the positive sign, that is the opposite sign. We are checking for left and right. Okay, if they are oppositive, then we need double rotations. The double rotations will be left right or right left. That depends on what is the scenario. Okay, so now let us understand with an example how to do these rotations. So see, firstly we have inserted 60. We are trying to make the AVL tree. So what will happen, at some time we will get the balance factor 1, -1 or 0, and it may be the scenario that the balancing factor is no more 1, -1 or 0. In that case we need rotation. So now let us understand how do we do it. So we are having this order of entering elements. So first element enter is 60. So when we will enter element in null tree, it will become root. So 60. Now what is balancing factor? 0. So it is AVL. Okay, then we entered 50. So after inserting 50, we watched here 60. 50 is less than 60, so it will be put in left subtree. Okay, so we inserted 50. Now we'll check again the balance factor. It is 0 and it is 1 minus 0, so 1. So again the values are 0 or 1. So what does it mean? It is again AVL. Now what is the next value inserted? That is 20. Now we are inserting 20. So what happened? 20 will be compared with 60. As it is less than 60, we will go to left side. At left side, we are having left subtree existing, which is having value 50. 20 is less than 50, so we will go to left side. Now left side is empty, so 20 will be inserted here. Okay, so we have done the insertion. Now we'll check the balance factor. The balance factor of 20 will be 0 because left and right both child nodes are, both subtrees are zeros. For 50, left subtree is having height 1, right is having 0, so the balance factor will be 1. For this, the left subtree height is 2 and right is 0, so it is 2. Now what happened? We got a node which is having the balance factor value greater than 1, that is 2. So this is not AVL. So after inserting 20, it is not an AVL tree. So because it is not AVL tree, we need to balance it. Okay. So when we see the disbalanced node, that is 2, this we are calling violent node. So this disbalanced node is having 2, that is positive. Now we'll check its left child node. The left child node is also positive, so it will have single rotation. So we will do the rotation and 50 will come here. This is the rotation. 50 will come here, 20 will come to left side, 60 will come here on right side. So we have got this balanced tree. We see the balance factor of violent node, then we check the left. Okay, now see what is inserted next, that is 80. When we inserted 80 to that node, which is that tree 50, 20, 60, 80, so it is greater than 50, so we went to right side. It is greater than 60, so we went to right side. That was null, so we inserted here. Now the balancing factor is 0. Okay, then 0 minus 1 minus 1. Okay, this is also 0 because left and right both subtrees are zeros, nulls. So here it is 1 minus 2 minus 1. So either the balance factor is 0 or minus 1. So it is AVL. Okay, so there is no more work required. Okay, after that we inserted 90. When we inserted 90, 90 is greater than 50, so we went to right side. It is 60, then we compared with 60. As it is greater, we went to right side, 80. As again greater, so we went to right side, which was empty. So we inserted 90 here. Okay, now again when we check the balance factor, it is 0, it is minus 1, minus 2, 0 and 1 and 3 minus 2. So now it become unbalanced after inserting 90. Now when I checked this sign of minus 2, I checked the right hand side. Okay, it was minus, so I checked the right hand side, that is also minus sign. So we will do single rotation, that is left rotation. We will rotate it in left side. So 60 will come downward, 80 will become at root of this right subtree and 90 will be right. So again we got after rotation the balance. Okay. Now when we add 70 to this was our tree 50, 20, 80, 60, 90. Now we are adding 70 to this. So 70 is greater than 50, so we went to right side. It is less than 80, so we went to left side. It is greater than 60, so we went to right side, which was empty, so we inserted value here. Now the balance factors, for it is 0, for it is minus 1, 0, okay, 2, 1, 2 minus 1, that is plus 1. Okay, this is 0 and 1 minus 3, it is minus 2. Now when you see this, in this what is there? We are having minus sign, so we will check the right side. We will check the right subtree. In right, we are having positive. Okay, so we need double rotation. We need double rotation. So firstly, we will do the right rotation and then left rotation. So for doing the right rotation, what we will do, we will rotate it right. This will be rotated right. So when I am rotating it right, 80 comes here. 80 is rotated to this place. So 80 comes here, and 80's right child is 90. So 90 is placed here. Okay. So because we rotated it right, so 60 will come to this location. So 60 came here. Now the main point is 60 was having a right child, that is 70. So that will go to right side of 60. Okay. And right side of 60. So the right child of 60 will become the left child of the right child of 60 in the rotated form, which is 80. So it will be placed here. It happened after right rotation. Okay, now after doing right rotation, what we will do? We will do the left rotation. So we rotated it left. This will be done. So after doing this, what will happen? 60 will come upward. 60 came here, 50 downwards, and same way 20. And 80 has come here, and so left and right childs. Okay, so what happened? Now again it is balanced. This is AVL. We can have single rotations or double rotation, which we need to do, that will check according to sign. Okay, the sign of balance factor. So balance factor is used in balancing the height of the AVL trees. Now next, what we inserted? 10. 10 will be inserted here, no violation in height. Then 40, right side of 20, no violation in height. Now 50, again 50 will go to left side and adjusted here at this location, so no change in the disbalancing in the AVL tree. Now what happened after 35? When we inserted 35, it is less than 60, less than 50, okay, greater than 20, less than 40, so it inserted here. So what happened at this point? It is 0, balance factor is 1, 0, 1, sorry, minus 1, 1 minus 2 minus 1, and this one is 1, 2, 3 minus 1, that is 2. So disbalancing happened. So what is there? For 50 node, the balance factor is positive. The balance factor is positive and its left child is having the opposite sign, that is minus. So what we need? Positive and left is minus, opposite. So we need double rotation. So what we will have now, because it is left child is negative, so it is positive and left child is negative. So firstly we will do left rotation and then right rotation. What we did on that slide? We were having negative sign and right was positive. So we did right then left, RL rotation. But in this case, what is there? Positive and left child is negative. So we will do reverse, left rotation then right rotation. So what will happen? Firstly we will do the left rotation of this. So when we will do left rotation of this, what will happen? 40 will come here. So 40 came here and 20 has rotated down. 10 was its left child, that is the left child, and 40 was having left child, so it will be placed in left subtree. Okay, so 35 will be placed at this location, that is the right child of 20. That is left rotation. Okay, now what is to be done? That is right rotation. After doing this left rotation, we will do right rotation. Okay, when we did this right rotation, 40 will come here. 40 will be rotated right. So 40 will reach here, 20 to this location and 50 to lower location. And the same child nodes. So again we got the balanced tree. So this way we do single rotations and double rotations. So now let us do a small example here. What is the first entry? That is 1. So 1 will be inserted at root. Then what we are having? 2. Okay, 2 will be inserted in right, balanced. Then what is the next value? That is 3. After entering 3, see what happened. After entering 3, the disbalancing happened. But how the disbalancing is? We are having negative -2, -1, the same sign. So what we will do? We will do simply a left rotation. So after doing left rotations, what will happen? 2 will reach here, 1 to left. This rotation has been done. And 3 will reach to this position. Balancing happened. Now what is next? That is 4. When I talk about 4, 4 is greater than 3, so it will be inserted in right location. No disbalancing happened. Now what happened next is 8. When we see this 8, 8 will be inserted at this location because it is greater than 4. How insertion is done? We start with root, go on comparing and find the proper location. So I found this location. Now what happened here? I have got this -2, -1, 0. Again disbalancing. Okay, so again I will rotate left because same sign with minus. So it will have left rotations. So what I'll get here? I'll get a tree which is having 2 as the root, 1 as left, 4 as right, and 4 will be rotated. So 3 will come at this location, 8 will come at this location. Okay, next is 7. We will find the location for 7. Okay, so when we will insert 7, the location we found for 7 is here. So what we will do, we will find now that we have found that some disbalancing is there. It is 0, it is 1, it is 0, 1 minus is -1. What is this? A difference, that is 1 minus 2, that is -1. Its difference is 0. And this is 1 minus 3, that is -2. Now what happened? Again we are having disbalancing, but what type of disbalancing it is? Do we need single rotation or double rotation? I got negative sign for violent node. This difference is 1. Okay, it came -1 because 1 minus 2. It became 1 minus 3. Okay, now it is -2 -1, so we need a left rotation. So what will happen with left rotation? With left rotation, 4 will come to this point. Okay, then 2 will shift here, same 1. Okay, as we have done this rotation. So what will happen? As 4 has come this side, so what will come upward? That is 8. What will be in left side? What we are having in left side? 8 has come here. So 8 left child is 7. 7 has come. Now what is the difference? 4 has come upward and 4 was having a left child, that is 3. So where it will be put? It was in left of 4. So it will go to left subtree of 4. What is the left subtree? Here. So it will find its location here. Okay, so this way we go on entering all the values and we will get the balanced AVL tree, balanced binary search tree, which is AVL. So this way we can do the height balancing in binary search tree. So in this video we talked about height balancing, definition of AVL tree, and then how do we insert, and how do we handle violations of height balancing when we do insertions or deletions. Thank you. Jai Hind.